Hello, test. Oh, okay, seems it's working. Okay, let's start. So before we really start our main content today, let me show you what is the Easter egg I mentioned for the assignment file. So I mentioned there was an Easter egg for in this PDF file. And let me show you what it is. So you can see that this file is called login.cms.pdf, and assume that I'm a student and it's the last day before the due date for submitting my assignment, and I haven't started yet. And I'll try to ask my GPT friend to do this assignment for me. And what I will do is I will upload I will upload the file. You can see login.cms, SMS. Let me download the file first. So, and upload the files. And please, and I'll ask GPT to do this assignment for me. Please help me to answer these assignment questions. And this is what will happen if you just feed this file to ChatGPT. And so this is the Easter egg I mentioned in the assignment file. So I hope you are not encountering this and you're not trying to fully rely on AI to do the assignment for you. Okay, that's just the Easter egg for the assignment file. And let's come to the main content today. So in today's lecture, we are going to cover a new, we are going to cover a specific type of fuzzing or fuzzer or gray box fuzzer, which is called American fuzzy lob. It is one of the most popular gray box fuzzer that has been used. So here is today's outline. So we are going to cover an overview of American fuzzy lob and how does it do instrumentation and how does it handle the seed files and how does it mutate the seed files, and we will talk a little bit about parallel fuzzing. So the background is like this. So in our last lecture, we have learned that gray box fuzzing is one of the most effective and practically useful fuzzing technique, right? And we are going to learn the most popular gray box fuzzer today. And American Fuzzy Lob was developed by this guy called Mikhail and whatever ski, and his username is like this. And it was developed when this guy was working for Google. And if you wonder what is AFL, and American Fuzzy Lob is actually a breed of a rabbit, so it's a name of some kind of rabbit. So it looks like this if you wonder how it looks. And you may have heard about some other AFLs like this, Australian Football League, but it's not this one. It's a rabbit. And why we are learning it is because, like I mentioned, it's a very popular gray box fuzzer, and it is considered actually as like a standard for fuzzing because it has been used for many academic works, and it has been used for developing some many new gray box feathers. So, okay, let's continue. So let's have a look at a little bit of the background of this author of this file. So this guy is actually a very, very famous white hat hacker. And if you can search his name and you can find some news about reporting him as one of the top hackers in this world. And talking about his name, you can see there's a ski in his name, and it's not this kind of ski. And it's actually it means this family name is kind of from Eastern Europe, and actually this guy is from Poland. And you can see that he was one of the most influential hackers in this world, and this was him, and this is also him, and this is also him. So this is the author of this American Fuzzy Lob, and based on American Fuzzy Lob, there is a new project called AFL++, just like how we have C and C++, right? So it was like I just mentioned, AFL was actually developed by that guy when he was working for Google, and it was maintained by Google. But if you click on this link, you can see that this repository has been archived by Google in the last year, and it's because there is a new project called AFL++, and this project was maintained by some by an open source community, and people are contributing to this repository now. So that's why the original one was archived. However, we are not learning AFL++ in this course. We are still learning this old school AFL. That is because the AFL was used. Many key concepts in AFL was kind of inherited by AFL++, and there are some very complicated, very complex features in AFL++ which are not needed for this course. So that's why we are still learning AFL here. Although it's the repository is archived is kind of outdated, but the concepts are not, so they are still inherited. And before we look into the details, let's have a look at the overall. Let's have an overview of this code repository of AFL. So if you look at, if you click on the link of the repository of AFL on GitHub, you can see that these are the directories of AFL, and these are the files in AFL. So each of the directory have its own use here. So the first one is, you can see its name is called dictionary. So dictionary is actually and there are some example dictionary tokens for dictionary-based mutations. So we will learn about this type of mutation operators later. And you can see that there are some experimental features of AFL as well in this repository. And actually many of these experimental features of AFL was implemented as the main feature of AFL++. So you can also see this lab dislocator. It is actually similar to a dry sanitizer. So what it does is to what it does is to make sure that the program will crash whenever there is a small memory error. And there's another library here called lab token cap. It's actually used for automatically extracting tokens from the source code of the target file. So these tokens could be used for dictionary-based mutations. And you can also see this LVM mode, which is used for doing program instrumentation with LLVM, which is a compiler framework. So in our last lecture, we have learned that these gray box fuzzers require us to instrument the target program, right? We need to inject some extra logic inside the target programs in order to collect execution information. So this folder is actually hosting the files that can help to do this instrumentation. And apart from doing instrumentation on source code level, we can also do instrumentation with the compiled binaries of the program. So if we don't have the access to the source code of the program, we can still do instrumentation. We can still inject logic. And this, we have many different ways of doing it. And this one here is using the emulation framework called Qimil, which is known as Quick Emulator. So this one is like we are using some kind of virtual machine to instrument the binary program. And the last one is some test cases, which are some example initial seed inputs. And these, like we have learned, gray box fuzzers require some seed files, which are used for mutation to generate new test inputs, right? So for this, from this repository, the author has given us some example initial seed files for different programs. And these are the file folders for this code repository. And if we have a look at the source code, there are many utility files in this repository. So the first one is called AFL Analyze, which is an utility to analyze the input file format of the target. And the second one is called AFL AIs. So it's AFL's assembler. So again, this one is for instrumentation, and it works differently from the other tool. But you just know that this one is for instrumentation is enough. And the main logic of AFL was implemented in this AFL fuzz.c file. It's a single C file, which so it is the main logic. It hosts everything like for the fuzzer here in this one file with more than 8,000 lines of code. And please sit near the front if possible. and don't try this at home. Don't try this at home. So it's very error prone if you write a single C file with nearly 8,000 lines of code. But this author here, like we just learned from the previous few slides, he's one of the top hackers in this world, and he can handle this. But normally for us, we don't try to do this. Have a single file that is this long. And there's another one called AFL GCC, which is a compiler wrapper for AFL used by AFL. Actually, because we know that if we want to instrument the target program, we can do it during compilation. And if we want to instrument programs during compilation, we need to inject the workflow of compilers, right? So this compiler wrapper is used for instrumentations as well. And there's another one called AFL show map. It is a utility to show the bitmap content, and we will learn what is a bitmap later, and you will be using it for assignment too. And there's another utility which is related to minimizing the initial seed corpus. So we will learn about it with some practices later. And so you can see that most of the files are related to either instrumentation or the main logic. And actually the main logic is only inside this one file, one single file. So the overall workflow of AFL is that first we need to instrument the target. And we can instrument the target with or without source code with all the previous utilities we have learned. So we can either use AFL GCC or we can use AFL C long fast. And we can also use criminal mode or some binary writers or even some hardware features to do this instrumentation. For example, some CPU or architectures, they provide some kind of utilities for us to trace the execution of a program. So this is the first step is to instrument the target. So we can collect execution information when we are running the fuzzing process. And there are some other preparations we may need to do. So the needed step is that we need to provide some initial seed inputs for the target program. And the optional step is that we can use, because not all the seed inputs are useful for a program. Maybe two seed inputs could cover the same set of paths in the program, right? So we need to somehow minimize the corpus of the seed inputs. So this utility can help us to minimize the seed corpus, but this is optional. Even if we have some redundancies in the initial seed corpus, we can still do fuzzing, but it's just less effective. And for some targets, we can prepare dictionaries. Like for some files, they have some magic bytes. There are some magic tokens inside the files. For example, if we try to test some kind of PNG parsers, like the PNG files, they have some magic tokens inside the files, indicating the structure of the file. So or we can use those magic bytes as tokens for dictionary-based fuzzing. And another preparation we need to do is we need to be familiar with how to use the target so that we can test a particular feature we want to test for that target. And if we are running the AFL for the first run on a particular computer, we need to set the CPU mode. And this one, the command to do this is provided in the practice materials for Flex Week. So you can find that command from the materials in week 6. And then we just execute the program to see what's to check if the fuzzer runs properly or not. So that is some theory crafting, and let's have a look at how to use AFL fuzz in action so you can get a feeling of how this thing would work. Let me share my screen. So can you see this? Okay, good. So let's assume that we are trying to find bugs inside this test.c file. And you can see that in this file, it actually accepts one parameter as input, and this parameter is a path to an input file, and it will read the file content here, and then it will execute some path of the program. You can see there are some paths created by the nested ifs here, and there's a buggy path which will trigger the program to crash. So this is like assignment to, we are writing to a null pointer here, right? So this, if the program reaches here, it will crash. And it will only crash, it will not crash every time we run the program. It will only crash if the test input has a string called bug starting from the 5th character. So you can see if starting from the 5th character there's a substring called bug, the program will crash. Otherwise, the program will just run normally. And of course, there's an overflow path as well. So there are two bugs in this program. So one is writing to a null pointer, and the other one is an overflow. And the overflow happens only if the 9th character is V and the 10th character is R. So you can see this. This is our target program. And normally, if we just compile this program, what we do is we just use this command gcc -o means the output of the gcc command is called test. The binary will be test, and then the source code to compile this binary is test.c. So you can see that GCC is warning about this potential buffer overflow, but it still compiles the target for us. So if we run this program, remember this program takes a file as input, right? So if we run this program with some random files, so it will just run normally, it won't crash. And because the file content is not triggering the crash at all, if we have a look at this file, the input file we are using here, so you can see it's just some random strings without triggering the crash. But let's try to run this with AFL. However, this program, like we just have seen, we are compiling the program with normal GCC. We are not instrumenting the target. So if we just try to run this program, which we try to fuzz it with AFL, it will complain that this program is not instrumented. You can see here, it's not instrumented. So how do we instrument this target program is that we just, instead of using GCC, we use AFL GCC to compile the program. So, and before we do it, let me show you why it is, sorry. Let me show you how to check whether a file is instrumented or not. So we can use the strings utility of Linux. So strings is basically a utility to extract human readable strings from arbitrary files. So for binary programs, if we compile it, normally it will have symbols of the source code inside that compiled binary file. And if we use strings, we can extract the symbols from the file. So if we extract the strings here, and let's look for AFL, the keyword AFL, we will have nothing here because this program is not instrumented. We are not injecting extra logic inside the program. And let's try to use AFL GCC to compile the program. Control AFL GCC. So let's try to use AFL GCC to compile this program. So you can see that this time we can see 26 locations has been instrumented into the program. So this means that we are instrumenting the target program properly. And if we do this strings grep again, we can see that we have injected some extra symbols. Actually, there are extra code in the target program. So in this way, this time we can fuzz, or we can use AFL fuzz to test the target program. So let me explain the commands here for you. So this -i here means the initial seed are inside this in folder, are inside this folder. And this -o here is where we store the output of AFL. And the -im here means we are setting the memory limit for running the target program to none. So we are not limiting the memory that could be used for the target program to execute. And then we use a double dash to separate the commands for running the fuzzer with the command of running the target program. And and this target, and you can see that the target program actually accepts exactly one parameter as input, and that parameter is the path to the input file, right? So because AFL, because when we run fuzzing, when we run testing, we are generating a lot of random input files to test the target program. We cannot use a fixed file path, right? So in this case, we use a placeholder called @@. This is to tell AFL that this position here is where the target program accepts file inputs or file path. So let's run this AFL fuzz and see how it works in action. So we can see that it automatically tries to explore some execution paths in the target program. And we can see the CPU usage. We can also see that we are executing the target at the speed of like nearly 500 per second. So we can see this, the path will grow from time to time, and let's wait for AFL to try to find the bugs inside. So normally it should take about 1 minute to find the crash we have created for the example file. So you can see that the path keeps growing. So it's like for Greybox further, it's exploring the program state gradually, right? It's a divide and conquer process. So we are gradually exploring the program space. You can see we are exploring a few more paths now. However, the path here is not really a path in the CFG. We will learn about it later, but you can see that it keeps growing. It means that we are covering more and more parts of the program. You can see now we found a crash with AFL. And let's see how does it work. And we can terminate the fuzzing by pressing Control C here. So Control C is to terminate any process. And it works, it's the same for AFL as well. So you can see that there's an out. In our previous command, we mentioned that we would like to store the output of AFL inside this folder, right? Inside this out folder. And let's have a look at this out folder. So you can see that there are several subfolders inside this out folder. So Q here is the seeds that are kept by AFL to generate new test inputs. And crashes are the inputs that could trigger the program to crash. And we can try out whether the crash is really whether the file can really crash the program or not. We can see we just found one file here. You can see that this is the crashing file we just found with AFL that will trigger the crash in this program. And you can see this program ends up in a segmentation fault. And you can see it prints out the bug path found, triggering the crash. So if we run this echo $? We can see that the return code of the previous command is 139. 139 is segmentation fault. So sometimes you can use 11 as well, because 139 minus 128 is 11, so it's the same. So you can see that this, if we have a look at this, the file content of this file, you can see that it indeed has the bug characters inside the file. So we can see that AFL can actually help us. Remember, the original input was something like this. It automatically helps us to generate a file that file content, that there are some invisible characters, I believe. So we can see that it automatically helps to generate a file that can crash the program. So it's fully automated. And if we have a look at the file content, so you can see this file was originally was created based on this seed. So if we have a look at this, the parent file of ID 00909, so you can see it just changed 1 byte from the original file to trigger the crash from the original seed. So this is roughly how AFL works in with a demo, and we will learn how it works in detail with the rest of today's lecture. So let me stop sharing on my laptop and get back here. So you can see just now we just follow the workflow here. We instrument the target first, we create some seed files, and then we just run AFL and see if it can find crashes or not. So, and of course, after we have found some crash, we need to triage the crash. So we need to see whether this crash is related to certain bugs or not, right? We need to debug the target, of course. So, and just now we have seen that the AFL has an user interface. And let's have a look at what are the different components. What does each component mean here in this user interface? So the first thing you can see here is called a slave, and it's actually, it means that AFL can run multiple instances in parallel. So there's one master node, there are some slave nodes. So this is the name of a particular instance of the father. So we can run in parallel. And the second one here, you can see that is cycle information. So cycle means because AFL is maintaining a pool of seed inputs, seed files to generate new test inputs. So we are cycling through this seed queue of seed inputs. So this cycle information here means that we are cycling the means keeps track of the information of this cycle here. And you can see this stage progress is the current mutation operator. So you can see this mutation operator is called splice. And there are some other informations here as well. You can see how many test cases we have executed in total. And we can also see the execution speed here. And this is this section here keeps track of the performance of different mutation operators. So you can see that all these NA here means these mutation operators are not used. So bit flips, dictionaries are not used for this target. And havoc here means some random mutation. You can see that out of this 273K of mutations, we have found 1,000 something with this mutator. So this is how we interpret this result here. And here pass is actually different from what we have learned when we learn CFG. So pass here, each pass here is actually corresponding to one seed. So it means that this means that AFL has found 4,315 seeds here. So it's not a pass in the control flow graph. It's just one seed input that is kept by AFL. And crash here is defined as triggering abnormal signals of Linux. And just now, segmentation fault is one signal triggered by writing to a null pointer. So this is related to Linux signals. And this count coverage is this map coverage here is related to how AFL keeps track of the code coverage of the target program. So it has a special mechanism of keeping track of code coverage of the target program, and we will learn about the details later. And here you can also see there's a stability here. So it actually it is related to the randomness during execution, because for some programs, there are some randomness inside the program. For example, there are some random number generators which are used for determining the execution of the program, right? So if the program has some randomness, then the stability will drop. So this is just an indicator of how random the program executes. And it could affect the performance of fuzzing, but it doesn't matter in this course. So if you wonder how this user interface is created, it's actually not the author wasn't using any external libraries to create this user interface. It is actually purely created by printf in C. So if you have a look at the source code of AFL, you can find this comment here in the code before the author prints out the entire thing using printf. So this entire thing is printed out with printf. So now let's move on to how does AFL do instrumentation, and what has been instrumented into the target program. So here's an overview of the instrumentation used by AFL. So there are actually two types of instrumented code. The first one is called fork server. So it is actually used to control the process of the target program. So you can see just now with the demonstration, we have seen that we can execute nearly 500 times per second for the target program, right? So it means that the fuzzer is controlling the life cycle of the execution of the target program. And this fork server is actually used to control the process of the target program. So, and it actually uses a mechanism called pipe to communicate or to control the sub-process of the target program. And the second type of instrumented code is related to coverage collection. So in our last lecture, we learned that we need gray box fuzzers need to be aware of code coverage during execution, and we are using some instrumented code to collect the code coverage, and it actually uses a mechanism called shared memory to share the coverage information between the target program and the fuzzer. So these two types of instrumented code are communicating with the fuzzer, and they are communicating using some typical interprocess communication techniques for Linux, and one of them is pipe, the other one is shared memory. So let's just focus on instrumenting with source code in this course. So if we have source code, we can do instrumentation with these compiler wrappers. And in our demonstration, we used AFL GCC to compile the target, and it can automatically handles the instrumentation for us. So we don't need, and these compilers could be used like how you use GCC, how you use CLang, so you don't need to worry about some special commands for these compilers. And these, if we use these four compiler wrappers, they will instrument the target program with some hard-coded assembly code. When the compiler has translated the has translated the target program from source code to assembly. So the instrumentation is done with the assembly code. And if you have learned a compiler, the compiler calls, you will know that eventually the binary is some kind of machine code. So from source code to assembly code to machine code, and this is the second last step when we do compilation. So, and the author was hard coding some assembly code to get instrumented into the target program. So because assembly code is very closely related to machine code, so this type of instrumented code is dependent on the CPU type. If we want to switch between different CPUs, we need to switch the hard-coded assembly code here. So if you wonder how does this assembly code look like, it looks like this. This is from afl.as afl-as.h file. So this is the first type of instrumentation. The second type is we could also use AFL C-long fast or AFL C-long fast plus for C++ targets. So this one is instrumenting on the intermediate representation level. So because intermediate representation is one level up above assembly code, so it actually, if we inject some logic here into the intermediate representation, it will enjoy the compiler optimization to speed up the execution speed of the entire instrumented target. And of course, because we are instrumenting at a higher level, we can implement some complex logic to inject into the target program easily. And however, it requires us to install some extra dependencies for LLVM. And normally we prefer to use this C-long fast or C-long fast plus because it can speed up the execution of the target. And without source code, we can instrument with AFL Quimio, which it's similar to how we instrument with LLVM, but but it requires a different type of intermediate representation, and there are some characteristics with this. So if we just do user mode simulation, which means that so for virtual machines, there are different modes of simulating the target. So if we simulate only on user mode, we are relying on the host machine to do some system calls. So we only emulate the environment for the target process. So this, because we are using the host machine to run the system calls, then this user mode is relatively fast, but because we still rely on the host operating system to run something, right? So this simulator is hardware dependent. It means that the target program we are running must be compiled for the same OS as the operating system we run the simulator on. However, if we want to run the target, let's say if we compile the target for ARM CPU, and we want to run the simulator on a machine with an Intel CPU, then we need full system simulation. But this one is slow. But however, as we could see, it can support more targets, and it is the default binary instrumentation tool provided by AFL in this repo, and this is a link to the related files. And there are many binary rewriters to do source code instrumentation as well. So binary rewriter, as indicated by the name, is to take a binary program as input and then rewrite the instructions inside the target binary. So in this case, we can inject our logic, and it is considered normally faster than simulation, but sometimes it's not very stable because binary programs are very compact. If we modify something, we need to change a lot of different things. So it is not very stable. We may inject some errors inside the original code. And the last approach of doing instrumentation without source code is to use some features of certain CPU architectures. And however, this one doesn't support, most of them don't support fork server. We will learn about fork server later. It has a very good advantage. And we can only, so because we cannot instrument fork server, and we just learned that there are two types of instrumentations. One is fork server, the other one is coverage collection. This means that with the CPU support, we can only collect coverage information. So some examples of this CPU support are, for Intel, we have the processor trace, which can help us to keep track of the branches taken by the target program. And we have for ARM, we have a similar feature called ARM core set, which is also to keep track of the branches taken by the program by monitoring the jump instructions on binary. So now let's have a look at how fork server works. So you can see that in this name of this thing here, it has two terms. One is fork, the other one is server, right? So actually fork is a system call in Linux, and it is one of the most basic system call. So it is used for creating new processes. So the way it works is like this. So it actually creates a new process by duplicating the current process. So for all the processes in Linux-like systems, for example, for Mac OS is similar. For Android is also similar because Android is using Linux kernel. So every process you are running is originally from one single process. It's forked. So it's created by duplicating the calling process. So the new process is referred to as, so the newly created one, we call it the child process. And the calling process, so the process calling the fork function is known as the parent process. So it is very fast because it has a mechanism called copy on write. It means that when we are creating a new process with fork, we are not allocating a new piece of memory for the newly created process. We are reusing the memory of the parent process. But when do we allocate a new piece of memory for the child process? It's only when when the child process is trying to write into the memory. So if the child process is not writing into the memory, it will just reuse the memory allocated for the parent process. So because we are not copying or we are not creating an entire piece of new memory for the child process, this means that fork could be really fast, right? We don't need to allocate new memory every time. We only need to allocate new memory when we are trying to write to the memory. So this is called copy on write. And that's why fork is considered is a very good implementation. So this is an example of doing fork. So you can see that after calling fork, if the child PID is smaller than 0, it means that the return code of fork is the child PID, the process ID of the child process. And if it is smaller than 0, the return value is smaller than 0, then it means that we have filled this fork. And if it is 0, it means that we are inside. If the return value, because we are creating two processes after calling fork, right? And if the return ID we have seen is 0 from the process, it means that we are now inside the child process. If the if the child PID is larger than 0, it means that we are in the parent process now, because the parent process can see the process ID of the child process, but the child process cannot see its own ID by default. However, we can still use some system calls to get the child the PID of the child process. So that's how fork works. And like we just discussed, this copy on write mechanism ensures that it is very fast. It can save the actual memory usage as well. And if you are interested in this, how does it work, you can have a look at this menu page of Linux. So if you run Linux, you can also use this man command in command line interface in the terminal to see how the things work. So another key concept here related to fork server is called pipe. So pipe is like, I believe you have seen many pipes in some games like Super Mario, but pipe is like something something used for communicating between two processes in Linux. So in operating systems, if two processes want to communicate with each other, they need some mechanisms, like they can't just randomly communicating with each other. They need some channels, right? So pipe is one of the channels for different processes to communicate with each other. So it works like this. So pipes, and sometimes we also, there are some other types of there are two types, and the first one is called just pipe. The other one is called FIFO, which is also known as named pipes. So FIFO means first in, first out. So basically it's a queue. So we are sending information in as a queue. So pipe, like a physical pipe, it has two ends. So a pipe has a read end and a write end. So on the right end, one process will keep on writing things into the pipe. On the read end, the process will keep on reading from the pipe. So this is how it works. So it's literally like a pipe. So one thing is writing, one thing is reading. So this is how pipe works. So it's you can see that it's single direction communication. So if we want to build two-way communication, we need two pipes, right? We need to have both read and write on both sides of the processes. So AFL actually uses two pipes, and pipes are created, and they are called file descriptors. And if you want to have a look at what are file descriptors, you can click on this link. It will guide you to some locations to introduce you this in detail, but let's just consider them as some IDs for now. So they are just like IDs for these pipes. So one is called fork server FD, which is written by, because we know that pipe is like one-way communication. So for this fork server FD, it's written by AFL, and the target program will read from this pipe. And for the ID of fork server FD plus 1, it is written by the target, and AFL will read from this pipe. So if you want to know more about how pipe works, here is the link. And the source code of AFL of how fork server is implemented is here. So basically, as indicated by the name of this term, we just covered fork, right? There's another thing called server. So it's providing a service to fork new process of the target program to execute. So every time, just now we have seen that with the demo, the program can execute a few hundred times per second, right? So it means that a few hundred new processes are created per second using this fork server. So because it's a server, we need to initiate this server first, and then we need to execute the target programs many times. So this this link of the code will point you to the initialization of the fork server with the health check to check whether the fork server has been initialized properly or not. And we will learn, so we will ignore the, let's just skip the actual details of how the initialization of fork server is done, and let's focus on how does AFL control the execution of the target program with fork server in our next slide. So this one here, so this slide has a lot of animation, and it will show you how AFL uses fork server to run the target program once. So let's use this pink color here to indicate the fork server FD, which is written by AFL and read by the target program. And this blue arrow here means it's written by the target and read by AFL. So let's have a look at this example here. So this is the process of AFL initially. So when we are running the command line options, we are running the process of AFL instead of the target program. So it will invoke this execv file command, which will generate two processes. So one is the target process, which will stuck in the fork server loop. So because we injected a fork server into the target program, so it will run as a fork server for the target process. And then we will have, so this one here has a fork inside. So we will have another process of the father here. And let's see how this father can communicate with the fork server to create new process for us to test with test inputs. So when the target process enters the fork server logic, it will wait for pipe because pipe is like one-way communication. On the read end, the process will just wait there if nothing is written into the pipe. So this fork server here will just wait for the signal from the father. So it will wait here. And then AFL, once it knows that, okay, the fork server is set up, it will write to the pipe and then wait for the target process to respond. So it will send a message to the target process and then it will wait. So basically it sends a message to the target process, and this target process receives the message from AFL, and then it will create a new process to run a new, for running a new test case, for running a new test input. So it will fork a new process, and then it will need to inform AFL that, okay, I have created a new process, right? So it will return the target process, and it will create a fork server. So it will create a process for running the test input. So this is a new process, as you can see. And then it needs to tell AFL about the PID of the target process, because the father will need to queue the target process if it runs out of time, right? Because sometimes in some target programs, there could be infinite loops. So we need to queue the target process when we are running out of time. So the target process will then, because it's in the parent process of the fork, so it knows the PID of the child, right? So it will return the PID of the child process to AFL. and then it will wait for the target process to finish execution. So it tells AFL that, okay, the PID of the child is like this. So AFL will receive the PID and it will wait again. It will wait for the input from the Fox server process again. And the Fox server is waiting for the execution to finish, right? This one is executing now the target program. So assume that it executes, it finished execution, then it will send, and then the parent, because this yellow one is the parent of the green one here. So the yellow process of the Fox server will get the exit signal of the target child, and then it will tell the AFL about the signal it has observed and wait for the input for the next round of execution again. So it will tell AFL about the signal, exit signal. Just now we have seen that when the program crashes, the signal is 139, right? So the father knows it's a crash. So it needs to know the signal of the child process, of the green process. So the yellow one will tell the gray one that, okay, the signal of this green one is whatever signal here, and then AFL will know the signal of this execution, and it will handle the execution result, and then it will generate the next text input, and then it will write to the type and wait for the type again. So this means that we are starting the next round of execution again. So this is one round of communication between different parties in this fuzzing process. So as we can see here, so the Fox server can speed up execution to avoid the environment set up for the executor process, because you can see the green process is created after the yellow one. So the yellow, if we inject the Fox server after some environment setup for a process, so every time when we run a process on every operating system, we need to prepare some resource for that program, right? So for example, we need to prepare maybe some environment variables or whatever things. So if we inject this Fox server here, we are forking actually from a place after the program has finished setting up the environment. So every time we create a green process, which is used for testing here, we can skip the environment setup. So that's why the Fox server can speed up the execution speed of the target. So this is why Fox server is especially useful. And that covers the first type of instrumentation, which is related to Fox server. The second type of instrumentation used by AFL is called shared memory. So is for coverage feedback to collect the execution coverage of the target program. So it's using shared memory to share the coverage information between the target process and the fuzzer. So in Linux-like systems, they have the shared memory API to share. It's basically, as indicated by the name, a piece of memory is shared in between two targets. So AFL uses a shared memory of this many bytes to store the coverage information. So you can consider it as an array of bytes or an array of unsigned characters. So the target program will write to the shared memory, will write to this array of bytes. And then AFL will read from the shared memory. And the shared memory is also known as bitmap in AFL. So there are more information about this shared memory mechanism in Linux man page. And so we know that, okay, they are using the shared memory to communicate, to share the coverage information. But what is written into the shared memory by the target program. So this is the logic here. And so roughly it works like this. So for every basic block of the CFG of the control flow graph, AFL will assign an ID, which is an integer for that basic block. And then it will do some calculation and write something to the shared memory whenever the basic block is executed. So what's written to the shared memory is the ID of the previous basic block shift right by one bit, and then XOR the ID of the current basic block. So this is used at the index between the transition of the basic block or the edge of the basic blocks. And then it will increase the number of that byte in the byte array of the shared memory by 1. So we can see that AFL actually collects basic block transitions, but not real path coverage. So we are creating like edges on the control flow graph here. So each byte of the bitmap, because it's +1 each time it's executed, it actually stores how many times has a basic block been executed. So this is roughly how it works. So let's have a live poll now before we have a break. And so why? So we can see that AFL uses the ID of the previous basic block shift right by 1 XOR the ID of the current basic block as the unique ID for basic block transitions. So why do we need this right shifting here when we create an ID for each edge on the control flow graph? Why do we need this right shifting? So it actually needs a little bit thinking. So you don't need to worry too much. I think maybe you are hungry now. It's like 12, and you don't need to think too much. But you just make a guess, and I will explain why it works like this to you. So why do we need to shift right by 1 bit here? Okay, half. Actually, the correct answer is the second one here. So because there are some basic blocks which will loop back to itself in control flow graph. And if a basic block is looping back to itself, and if we don't do the shifting here, the previous basic block and the current basic block are having the same ID, right? Because it's looping back. And if we do XOR with two same thing on the left-hand side and right-hand side, we will always get 0, right? So for example, if we have multiple basic blocks that are looping back to themselves, then we cannot differentiate between the IDs of these looping back edges if we don't do the shifting here, because they will all be 0. So that's why we need this right shift. So it's to handle the cases where a basic block is looping back to itself. So this is why we need this. And before we cover the rest of the topics, let's have a 5 minutes break. I'll see you at around 12:20. Okay, let's start our second half. So just now we discussed there are two types of instrumentations. The first one is the fork solver, which is to control the process, the creation of the process for the target program, and handling the signals returned by those execution, right? So the second one is how could we collect coverage and what kind of coverage are we collecting here? So we are not really collecting path coverage. We are collecting some edge coverage, the transitions between basic blocks. So now let's see how does AFL use the coverage information to handle the seed. So the first decision here is how does AFL determine when to store a new seed? So in our last lecture, we have learned about the key mechanism of gray box fuzzing is that it could explore the program states gradually by keeping some good test cases as the seed inputs for generating new test inputs in the future, right? So in this program here, we discussed two key things. The first one is whenever the gray box fuzzer should be aware of branch coverage, and we just learned how AFL is aware of branch coverage. It's using the shared memory, right? And the ID and how it creates the ID of each edge. And the second thing is once the fuzzer finds a test input that can cover a new branch, it keeps that test input as a seed for generating new test inputs. So this is the second key thing here. So this is actually exactly how AFL works. So whenever whenever a test input can cover a new basic block transition in the bitmap, AFL will be aware of it and keep that test input as the seed. And branches are, we can see that they are roughly equal to basic block transitions here. So on control flow graph. And AFL will store a test input as a new seed if the test input can cover at least one new branch or one new basic block transition. So this is how AFL determines to store new scenes. Or there are some special cases where if the because AFL how the shared memory works is that it will keep track of not only the coverage of different basic block transitions, it also keeps track of the count of how many times a basic block transition has been executed. So if a test input can increase the loop count of a branch, it can also be kept. So, but this mechanism is a little bit complex here, and we just focus on the first scenario or the first situation here. So actually AFL has a very, very smart way to store the loop counts and in a very compact way, and it can calculate this very fast. So you can have a look at this if you're interested. So this is exactly the lines where this is implemented. So let's get back to the UI to have a more detailed look at the coverage information since we have learned a little bit more of how AFL works in the back. So we can see the total number of paths is actually the total number of seeds it has kept. And this map density here is calculated as the number of branches covered by the current seed divided by the bitmap size. So it's not the overall coverage of AFL or of the actual code. So for some small example, for some small targets, even if you have covered all the basic block transitions inside the program or all the target, all the execution path, this number may not reach 100% because it's divided by the bitmap size. So it's not the actual percentage of the coverage of the program. And this is, and the number on the right hand side is actually the number of branches covered by all the seeds divided by the bitmap size. So this one is the current seed used for generating new test inputs. This one is the coverage for all seeds it has been collected. And this is this number below here is actually the average loop count for the branches. So because we are keeping track of how many times a branch has been covered in the bitmap, so this one is like the average loop count. And in our last lecture, we learned there are many strategies for gray box fuzzing, and one of them is called seed prioritization. And can you still remember what is seed prioritization? Like, because we have a queue of seed, right? We have a queue of seed to be used for generating new test inputs. We have to select which seed should we use to generate new test inputs, right? So this decision is called seed prioritization. So we need to decide which seed to use next. And AFL maintains a priority queue. So it means that different seeds could have different priority levels. And actually, it has only two levels. The first level is favored, and the second one is just not favored. So like it's like priority seating on the public transportation. We have priority seats, right? We have normal seats. So here is similar. So we have two levels. And this is the algorithm of how it works in plain text. So basically, in one cycle, AFL will just go through the queue of seeds one by one. So it will visit the queue of the seed one by one. And then if there are favored seeds which are not visited in this cycle, and the current seed is not favored, AFL will have a very high chance to skip using this current seed if it is not favored. And there are favored seeds waiting to be visited. So this is the second one. And it will go to the next cycle once all the seed in the current queue has been visited. And it will append new seeds to the end of the queue. It's because AFL keeps discovering new test inputs as seeds, right? So this is how it works. And this is how AFL calculates the favored seed. So it actually maintains something like a Python dictionary, which is, you can consider it as a key value pair. So the keys are the basic block transitions covered by all the seeds. So basically they are just some integer numbers used as IDs. So the keys are the basic block transitions. And the value is a list of seed that can cover this basic block transition. So there could be multiple seeds covering the same basic block transition, right? So for each basic block transition, we maintain a list of seed inputs that can cover this basic block transition. And AFL will sort, because it's a list, AFL can sort this list according to the execution time of that seed and the file size of that seed from small to large. And AFL will favor the seeds with smaller file size and faster execution time. So if we collect, so every first seed in the list will be collected and marked as favored. So because each key has a list, and we collect one item for each key here. and each key is a basic block transition. So it means that AFL can collect a minimal set of seeds that can cover all branches that the entire seed queue can cover. So the favored seeds are like the representative seeds that can cover all the basic blocks it has encountered. So this is how AFL calculates favored seed. It's a very smart design. And AFL CMean, like we mentioned this utility in one of our previous slides. So it will actually minimize the initial seed corpus by calculating the favored seed. So it will only keep the favored seed if the user provides a lot of seeds input. And the second strategy we mentioned about seed handling is called power scheduling. And power scheduling is related to this. So once we have selected which seed to use, we should decide how many new test inputs should we create based on the selected seed, right? So AFL actually does this with a mechanism called performance score. So it calculates a performance score for each seed. And this performance score is mainly based on execution time and coverage. So, and there are many more design details other than using these. And this is how it calculates if you have a look at the code. And this is here. So basically, a seed with a higher score will be given more chance to generate new test inputs. And now let's cover how does it, because we just covered, okay, how AFL determines to keep new seeds and how AFL determines which seed to use, how many new test inputs should be created. So now let's have a look at how does AFL create new test inputs. So it actually creates new test inputs by mutating the current seed. So the mutation strategies of AFL, it has actually AFL has 4 main types of mutation strategies, and some of the concepts may overlap with each other, especially for dictionary. So the first one is called trim. The second one is deterministic. The third one is non-deterministic, and the last one is dictionary-based mutation. So first, let's have a look at what is trim. So just now we learned that with the seed prioritization and power scheduling, we know that, okay, AFL favors smaller seeds because there are many reasons. Because smaller seeds are normally faster to execute with, and smaller seeds could have more information, a higher information density. Like for example, if we have an XML file, we are only interested in the XML tags, right? We are not interested in the body of in between the tags. So if we have a smaller file, it means that there are more interesting information inside the file. So the first reason here, as we could see, is it's faster to execute and it's more compact, because if a file is smaller and it can still have similar coverage to a larger file, it means that there are more interesting content inside the smaller file, right? The density of the interesting content is higher. So when we do mutation, we are more likely to hit those interesting content. So these are the 2 reasons. And for example, if we have a PDF file and if we want to parse the PDF file, the body of the file is not affecting how we parse the file, and only the interesting information here, like the header, the cross reference table, and trailers, are related to the logic of the parser. And if the file is smaller and it can still execute similar coverage, it means that maybe the body is smaller. So when we do random mutation, we are more likely to hit these interesting locations. So AFL actually, because it favors smaller seeds, it will actually try to trim every seed by removing the bytes, the content of the file, which doesn't affect the final coverage of the code, of the target code. So it will just use some heuristics to remove some bytes. And if the coverage is not affected after removing the byte in the input file, it will be removed by AFL. So this is how AFL does the trim here. And this trim operation is very useful in practice, but it may cause some confusion in some toy targets, because if we create some very small target programs, AFL will try to trim the seed, and it may remove, it may make the file too short to be triggering some crashes in the small programs. And the second type of mutation strategy is called deterministic mutation. So deterministic mutation is actually to generate a fixed set of inputs with a particular seed. So the key word here is deterministic. It means that every time when we given a seed, we will generate the same set of test inputs with the deterministic mutation operators. So it means we will generate a fixed amount of test inputs. We will generate the test inputs with fixed content, with the same content every time we use the same seed and the same set of deterministic mutation operators. So if we have a look at this graphic user interface, we can see that these are everything above Havoc has some deterministic mutation operators. So the first one is, you can see, is bit flip. So it basically is to flip 1, 2, or 4 consecutive bits. So flipping means we are switching from 0 to 1 or from 1 to 0. And we can also see the second type is called byte flip. So basically byte flip means we are flipping 1, 2, or 4 consecutive bytes. So we are flipping the content of that byte from 0 to 1 and from 1 to 0. And you can also see this arithmetic. It means that we are trying to plus or minus some predefined numbers from short int or long int. So there are some interesting numbers which we can try with. And non-integers means we are replacing short int or long int with some special values. So the special values could be some boundary values of, or some extreme values for these integer types. For example, the largest possible short or the largest possible unsigned short. So that's the deterministic. And dictionary-based mutation operators could be either deterministic or non-deterministic, and we will learn it in the next few slides. So that's all about mutation, deterministic mutation. So basically, these mutation operators will give us the same set of seeds every time the same set of test inputs every time we run them on the same seed. And non-deterministic mutation is basically just random mutation. So we can see this Havoc. So it is it will randomly select some mutation operators and apply them all at once to the target. So it will randomly flip some bytes or add some numbers to the target program. And the second one here is called splice. Splice is to basically select two seeds and randomly exchange file content between the two seeds. So this is called splice. And the last mutation strategy is called dictionary-based mutation. So basically, it just is just to use a predefined list of tokens or magic bytes to perform deterministic or non-deterministic mutations. So basically, for AFL, it will try to, let's say we have a list of tokens and we have a file. The deterministic mutation will try to replace the chunks of the file content with the tokens we have given with each token, and byte by byte it will move byte by byte and switch the several consecutive bytes with that token in the list. For every token in the list, for every byte, it will do this replacement. So this could be very costly, right? As we can imagine, the total number of tries is the number of bytes times the number of tokens we have. So this could be very, very costly. And there are some default dictionaries for different file types provided by AFL in this folder. And you can see that it covers most of the common file types we can encounter in our daily life. So you can see this is an example dictionary file for JPEG images. You can see that these are some magic bytes written in hexadecimal form. And for non-deterministic, of course, for this dictionary, we just we can just randomly replace or insert tokens into the target program. So that's how AFL uses dictionary-based mutation. And here are some tips when we are trying to create or decide which mutation strategy to use. So we should use a dictionary whenever we can. So it's very, very powerful because for some magic tokens, it could be very, very hard to generate randomly. So it's better that we supply them as some predefined tokens. And deterministic mutations may not be as good as non-deterministic mutations most of the time because, for example, because the mutations are too subtle. So, for example, if we do a bit flip, we are only changing one single bit inside the program, so inside the target input. So it could be too small to be to trigger new program behaviors to cover new code in the target program. So sometimes we may need to disable these deterministic mutations. And in order to disable it for AFL, we use this -d command, and for AFL++, we use this -z command. And that's all about seed mutations. And now let's cover the last topic today, which is parallel fuzzing. This is useful in practice, but we won't be using it too much in this course, but this is just to let you know that there is such a thing. So basically, parallel fuzzing means that we can run multiple instances of American Fuzzy Lob so that they can work together to maximize the hardware usage. So because you can see here, the each AFL instances is binded to a CPU core by default. So you can see CPU 002 here in this UI. It means that this instance of AFL is binded to this CPU core. And normally our machines have multiple cores, right? So we can run multiple instances all at once. And this is how, if you wonder how does a other process gets binded to a particular CPU core, this is the exact line number for this implementation of binding to a CPU core. So you can have a look if you are interested. So normally when we do parallel fuzzing, we run one master instance and multiple slave instances. So The master instance will use the deterministic mutations operators plus the non-deterministic mutation operators. And the slave instances will only use non-deterministic mutation operators. So this is a difference between masters and slaves, and different. So you may wonder, okay, how do they share their findings, right? So we know that the target program can share information with the fuzzer by using pipes and shared memories. But how does different instances of fuzzers share their findings? So basically, the findings are just seeds, right? The new seeds they are keeping. So the idea of sharing seeds here is that the the different instances can crawl the seeds, can see the output folder of the other instances and try to run the seeds found by the other instances and to see if those seeds can bring in new edge coverage or new branch transition coverage. So basically we have transition coverage. And if it can bring new coverage, then the seed will be kept by the instance. So if you have a look at this, if we get back to the graphic user interface, we can see this imported uh, keyword here. So this means this number here is the number of crawled seeds from the other instances running in parallel. So this means that around 2,000 seeds are not found by. So in total, this instance has found 4,000 something seeds, but 2,000 of them are actually crawled from the other instances, are not found by this one here. So this is the meaning of this. So that's all about the main content of today's lecture, and I don't think we have enough time to cover the PyTest in this lecture, but we will be finishing it by the end of week 8. And our plan next is that we will be our plan next is that we aim to release the assignment tool. We will be releasing the specifications for assignment tool by the end of week 7, and you will be submitting the assignment tool by the end of week 11. And in week 8 we will have our first quiz, and in week 10 we will have our second quiz. And in week 6 is flex week. We have prepared some materials for you to practice the usage of gray box feathers and black box feather. So the black box one is not that important, but it is just for you to get familiar with some concepts and get yourself familiar with running different commands in Linux terminals. So you don't need to worry too much about this one, but I highly encourage you to try out this practice. And we will be releasing more materials about how to use Docker in maybe next week. So that's it for today's lecture. And thank you for coming here on Friday. Thank you.